In this video, I want to have a look at some graphs of trigonometric functions. So we have already had a quick look at the graphs of sine, cos and tan when we started looking at trig functions, and we were looking at those graphs in terms of degrees. So today I want to look at those graphs in radians instead of degrees, and I want to have a look at those graphs when they're not just the most basic y equals sine x or cos x or tan x. So the first function that I want to have a look at is sine of x. So that's this blue wave here. So you can see that it's got the shape that we looked at last time, but instead of our degrees along here, we've got our radians. So we can see that sine has a value of 1 at pi over 2, which is equivalent to 90 degrees. Sine of 0, sine of pi, and sine of 2 pi, so 0, 180, and 360, are all 0. And sine of 3 pi on 2, so sine of 270 degrees, has a value of minus 1. And you can see that this wave is going to repeat itself over and over and over again if we zoom out. All right, so that's sine. Let's have a look at cos. So cos has that same sort of shape. It has exactly the same shape as sine, but it's been shifted along our axes a little bit. So instead of having a value of 0 at 0, it's going to have a value of 1 at 0. At pi on 2 or 90 degrees, it's going to be 0. At pi or 180, it's going to have a value of minus 1. Then at 270 or 3 pi on 2, it's going to have a value of 0. And at 2 pi, it's going to be back up at 1. So the same shape as sine, but it's been shifted along that axis. All right, let's have a look at tan of x then. So you can see here that there's lots of different sections to our graph. It's not one continuous wave this time. So what that means is that it's going to have a whole pile of asymptotes. So there's an asymptote at pi over 2 or 90 degrees. It's also got another one at 270 or 3 pi on 2 as well. So every 180 degrees starting at 90 degrees, we've got another 180, there's another asymptote. Got another 180 and there's another asymptote there as well. And that pattern repeats itself forever as well. Now I also wanted to have a quick look at the reciprocal ratios. So our first one is, we're going to have a look at is cosec. Now cosec looks like this, and it's the reciprocal of sine. So if we put sine back in there, you can see how the two graphs are related. So whenever sine was equal to 0, so at 0, at pi, at 2 pi, there's going to be an asymptote for cosec. Now just like sine and cos are very similar functions, cosec and sec are very similar as well, but again, they've been shifted over. So you can see how the values, when our original function was 0, our new function has an asymptote at those points. All right, now last one, if we compare tan and we compare cot. So they're very similar, but they've been reflected. So now where we had an asymptote, we have a 0, and where there were zeros, there are now asymptotes. So that's cot, and this is tan. I should have made them a different color. Okay, there are a couple of new terms that we need to know. The first one is the amplitude. So the amplitude of a wave is the maximum height that a wave reaches above its center. So if we jump back to our graphs, now tan isn't a wave, so it's not going to have an amplitude, but sine and cos both will. So the center of our graph in this case, in just your basic sine function, is y equals 0. And we can see that the maximum height that it reaches is 1, and the maximum height, the minimum height that it reaches is minus 1. So that means that sine has an amplitude of 1, and cos will also have an amplitude of 1 as well. And the next term we need to know is period. So the period of a function is the distance that that function covers before it starts to repeat itself. So let's have a look at our graphs. So if we just have a look at sine first, if we started at 0, we can see that it goes up, goes down, and then gets back to its starting point at 2 pi. And then it's going to repeat that pattern. So we've got one sort of chunk of that pattern here, and then it repeats over and over again. So every 2 pi units along, that graph is going to repeat itself. So that means that sine has a period of 2 pi. Let's have a look at cos. So it starts up here, we're going to go down and back up to that same value at 2 pi, and then it's going to repeat itself until 4 pi, and then again until 6 pi. So it's repeating itself every 2 pi as well. So that means its period is 2 pi. Our next one, tan. Now tan's a little bit different. So if we see it's at 0 here, it's going up, and then it's coming from down here and coming back up to pi, so where it started. So you can also look between the asymptotes for this. So say we started at pi over 2 instead. You can see this squiggle, this part of the function, and then it stops again at 3 pi on 2. So the period for tan is just pi, whereas for sine and cos, it was 2 pi. So those amplitudes and periods only apply to the basic sine, cos, and tan, or the basic trig functions. But sometimes our functions are more complex, and it's going to change the period and the amplitude. It's going to stretch it either horizontally or vertically. So we want to have a look at how different values affect the period and the amplitude of our functions. All right, so what I've done, I've added in some sliders into GeoGebra. So we've got A and B. I'm going to change our functions a little. So we're going to have A times sine of bx. So we've changed our function. Now in this case, we've got A and B set as 1. So if we graph this, this is just our original function sine x. If we change our A, we want to see how that's going to affect our graph. So we're going to make A get bigger, and you can see that our function is getting taller. So for example, when A is 4, our graph is now coming up to 4 and down to -4. So this A is affecting the amplitude of our graph. Right, if we put that back at 1, now we can see what B does. So B is the number that's inside this bracket, the coefficient of x inside that sine function now. So if we increase that, you can see that it's squishing our graph in horizontally, so it's making our period smaller. And if you take it the other way, we can stretch it out as well. So let's change it for a second. Let's move it up to 2 and see what's happened to our amplitude. So before, for sine and for cos, our period was 2 pi. So our graph came up, down, and back up, so we went through one cycle of that wave by the time we got to 2 pi. Now that we've moved it up to 2, we can see that it's happening twice in that time period. So that wave is occurring twice before we get to 2 pi. So what that means is that with this 2, our period has halved. So our period now, instead of being 2 pi, is just pi. If we say move this up to 4, for example, you can see that now between 0 and 2 pi, our wave is occurring 4 times. So our period then would be pi on 2 instead of 2 pi. So that would be a quarter of our original. Now that same sort of effect is going to happen with cos and tan as well. So the coefficient of the number is going to affect the amplitude, and the coefficient of x, so the number that's in the trig function with that x, is going to affect the period. So if we write that more generally, we can say y equals a sine bx and y equals a cos bx have an amplitude of a, so that coefficient, and they have a period of 2 pi divided by b. Now tan, we know that has no amplitude, but if we have y equals a tan bx, then the period is going to be pi over b. All right, so when you're given a function and you're asked to graph it, you need to be figuring out what the amplitude and the period are, and then using those to help you sketch that trig function.